So here's something kind of wonderful to think about as you settle in tonight. Every time you watch a ball arc through the air, every time water curves over the edge of a fountain, every time you notice the way sunlight fades gradually at dusk rather than just snapping off like a switch, you're watching calculus. You're watching the mathematics of change, of things becoming other things, of quantities that refuse to sit still. And the beautiful part, the really beautiful part, is that for most of human history, people watched those exact same things and had no formal language to describe them. They could feel it. They could sense that something deep and mathematical was going on. But they couldn't quite pin it down. It took thousands of years, and some of the most stubborn, brilliant, complicated people who ever lived to finally build the framework we now call calculus. And tonight, we're going to walk through that whole story slowly from the very beginning. Let's start where it makes sense to start, with the ancient Greeks, and with a problem so simple that a child could state it, and so profound that it essentially haunted mathematics for 2 millennia. Imagine you have a circle, just a plain, ordinary circle, and you want to know its area. Now, you probably remember from school that the area of a circle is pi times the radius squared. That formula feels like it was always there, carved into the universe somewhere. But someone had to figure it out. Someone had to look at this curved shape. A shape with no straight edges, no corners, nothing you could easily measure with a ruler, and find a way to calculate the space inside it. And the way they did it is, honestly, the first real glimpse of calculus in human thought. The person most associated with this is Archimedes, working in Syracuse on the island of Sicily around 250 BC. Archimedes was one of those rare minds that comes along maybe once every few centuries. He was a geometer, an engineer, an inventor, the kind of person who could design war machines to defend his city from Roman invaders and, in the same afternoon, sit down and work out the mathematics of floating bodies. But the thing that concerns us tonight is what he did with that circle. Here's the idea. You can't easily measure a curve. Curves are slippery, mathematically speaking. But you know what you can measure? Straight lines, triangles, polygons, things with flat edges. So Archimedes thought, what if I don't try to measure the circle directly? What if instead I fit shapes inside it that I do know how to measure, and I make those shapes get closer and closer to the circle itself? Picture this. You take a circle and you inscribe a square inside it, a square whose 4 corners just touch the circle. You can calculate the area of that square easily. It's smaller than the circle, obviously, but it gives you a lower bound. Now, instead of a square, try a hexagon. 6 sides. The hexagon fits inside the circle more snugly. Its area is closer to the circle's area. Now try a 12-sided polygon. Even closer. A 24-sided polygon. Closer still. Archimedes actually did this with a 96-sided polygon. 96 sides. And he did it by hand, without algebra, without decimal notation, without any of the tools we take for granted. Just pure geometric reasoning. And here's what's so striking about this. As you add more and more sides, the polygon starts to look like the circle. The difference between the polygon's area and the circle's area gets smaller and smaller. It never quite reaches 0. You can always add more sides. But it approaches 0. It creeps toward it. It tends toward it. That word, tends toward, is doing enormous work right now. Because that idea, that you can get as close as you want to some value without ever quite reaching it, that's the idea of a limit. and limits are the absolute bedrock of calculus. Everything in calculus, every derivative, every integral, every infinite series rests on this one concept. Archimedes didn't call it a limit. He didn't have that terminology. But he was using the idea intuitively, beautifully, more than 2,000 years before calculus was formally invented. He called his approach the method of exhaustion, which is a fantastic name when you think about it. You're exhausting the space between your approximation and the true answer. You're squeezing it out, leaving less and less room for error, until the error is so small it's essentially meaningless. And with this method, Archimedes was able to show that the area of a circle is exactly equal to the area of a triangle, whose base is the circle's circumference and whose height is the circle's radius, which, if you work through the algebra, gives you pi r squared. He got there, with polygons and patience and sheer geometric brilliance. Now, let's sit with this for a moment, because there's something philosophically deep happening here that's easy to rush past. Archimedes was dealing with infinity, not in a dramatic cosmic sense, but in a very precise mathematical sense. He was saying, imagine you could do this process forever, adding more and more sides to the polygon, and in the limit, there's that word again. In the limit, the polygon becomes the circle. But does it really become the circle? Can a polygon with infinitely many sides actually be a circle? Or is it always just an approximation? This question tormented mathematicians for centuries. It's the kind of question that sounds almost philosophical, almost like something you'd argue about over wine rather than in a mathematics lecture. But it turns out to be absolutely critical. Because if you can't make rigorous sense of what it means to approach infinity or to tend toward a limit, then you can't really justify any of the calculations that come later. The entire edifice of calculus wobbles without it, and it took until the 19th century, we're talking more than 2,000 years after Archimedes, before mathematicians finally nailed down a rigorous definition of limits. But we'll get to that part of the story later. For now, just hold on to this. Archimedes was playing with fire, mathematically speaking. He was using infinity as a tool, and it worked, and he knew it worked, but he couldn't fully explain why. He wasn't the only ancient thinker grappling with this either. About 2 centuries before Archimedes, there was a philosopher named Zeno from the Greek city of Elea, in what's now southern Italy. Zeno is famous for his paradoxes, and at least 2 of them cut right to the heart of what calculus would eventually need to resolve. The most famous one goes like this. Imagine Achilles, the great Greek warrior, the fastest runner in the ancient world, races a tortoise. The tortoise gets a head start, say 100 meters. Achilles is 10 times faster than the tortoise. So you'd think he'd overtake it easily, right? But Zeno says, think about it more carefully. By the time Achilles runs those first 100 meters to where the tortoise started, the tortoise has moved forward 10 meters. By the time Achilles covers those 10 meters, the tortoise has moved another 1 meter. By the time Achilles covers that 1 meter, the tortoise has moved another 1/10 of a meter, and so on, forever. There's always a little gap. Achilles is always chasing, never quite catching up. So, and here's Zeno's punchline, Achilles can never overtake the tortoise. Now, obviously, in real life, Achilles overtakes the tortoise. You know this. I know this. Zeno knew this. The paradox isn't really claiming that motion is impossible. What it's really doing is exposing a gap in our mathematical understanding. It's asking, how do you add up infinitely many things and get a finite answer? Because that's what's happening here. The distances Achilles has to cover, 100 meters, then 10, then 1, then a tenth, then 100th, form an infinite series. And if you add them all up, you get 100 plus 10 plus 1 plus a tenth, and so on. That sum is 111.111 repeating, which equals 111 and 1/9 meters, a perfectly finite distance. Achilles reaches the tortoise at exactly that point. But here's the thing. Being able to say that an infinite sum has a finite value requires the concept of a limit. You need to be able to say, as I add more and more terms, the running total approaches a specific number, and I can get as close to that number as I want by adding enough terms. Without that concept, you're stuck. You're staring at an infinite process, and you have no way to talk about its outcome. So Zeno, without meaning to, had identified one of the deepest problems in mathematics. And it sat there, unresolved, for a very long time. The Greeks were deeply uncomfortable with infinity. They used it cautiously in methods like Archimedes' method of exhaustion, but they always hedged. They always phrased things in terms of as close as you wish, rather than at infinity. They treated infinity like a loaded weapon, useful, but dangerous. And honestly, they were right to be cautious, because infinity is dangerous. It leads you into contradictions if you're not careful. It lets you prove things that are obviously false if you manipulate it without proper rules. The history of mathematics is littered with examples of brilliant people getting tripped up by infinity, making arguments that seem perfectly logical, step by step, but arrive at nonsense. The Greeks sensed this, and so they kept infinity at arm's length. They used it implicitly, but refused to embrace it explicitly. This caution had consequences. It meant that for all their geometric brilliance, the Greeks never developed calculus. They came close. Archimedes came astonishingly close. But they pulled back from the edge. They didn't take the leap of saying, let's just work with infinitely small quantities directly. Let's treat them as objects we can manipulate, and let's see where that takes us. That leap wouldn't come for a long, long time. After the Greeks, the mathematical center of gravity shifted. The Roman Empire, for all its engineering prowess, those aqueducts, those roads, those arches, wasn't particularly interested in abstract mathematics. The Romans were builders, not theorists. They could construct a dome that would stand for 2,000 years, but they weren't going to sit down and work out the mathematics of curves. That kind of thinking migrated eastward to the Islamic world, to India, to China, where mathematical traditions were flourishing in ways that Europe wouldn't match for centuries. And it's in India, actually, that we find some of the most remarkable early steps toward calculus, steps that are often overlooked in the standard Western telling of this story. In the 14th century, in the Kerala region of southern India, a mathematician and astronomer named Madhava of Sangamagrama did something extraordinary. He figured out how to express trigonometric functions, sine, cosine, arctangent, as infinite series. Infinite sums of terms that get smaller and smaller and converge to the exact value of the function. Think about what that means. He was saying, I can take something smooth and continuous, like the sine function, and break it down into an infinite sum of simple polynomial terms. Each term is easy to calculate, and if you add up enough of them, you get as close as you want to the true value. This is, in essence, the same idea as a Taylor series, which in Western mathematics is usually attributed to Brooke Taylor in 1715, more than 300 years after Madhava. Now, whether Madhava's work influenced European mathematicians directly is a matter of historical debate. The transmission routes aren't entirely clear, but the mathematical achievement is undeniable. Madhava and the Kerala school were doing calculus-adjacent work of a very high order, in relative isolation, centuries before Newton and Leibniz. And speaking of the Islamic world, there's another thread worth picking up here. Around the year 1000 AD, the great mathematician Ibn al-Haytham, known in Europe as Al-Hazan, was working in Cairo, and among many other things, he figured out how to calculate the volume of a solid of revolution. That's the shape you get when you take a curve and spin it around an axis, like spinning the profile of a vase to get the full three-dimensional vase. To do this, he essentially had to sum up infinitely many infinitely thin slices, disks, really, and add up their volumes, which is, if you squint at it, basically integration. He was integrating a function, using a method that Archimedes would have recognized, but pushing it further, applying it to more complex shapes and problems. These contributions matter. They matter because calculus didn't spring fully formed from the minds of two European men in the 17th century. It grew, slowly, across cultures and centuries, like a plant sending out roots in different directions, each root finding water in a different place. The Greeks gave us the method of exhaustion and the intuition of limits. Indian mathematicians gave us infinite series and early forms of what we'd now call power series expansions. Islamic mathematicians pushed the boundaries of geometric integration, and all of these threads would eventually weave together into something unified and powerful. But to get there, we need to move forward in time, to Europe, to the Renaissance, to a period when mathematics was about to undergo a transformation so dramatic that it would change not just how people calculated, but how they thought about the physical world itself. And the person who set that transformation in motion wasn't primarily a mathematician at all. He was a French philosopher with a famous stove-heated room and a habit of doubting everything. And his name was René Descartes. What Descartes did, and this might sound simple, but it was genuinely revolutionary, was he connected algebra to geometry. He showed that you could take a geometric curve, any curve at all, and describe it with an equation. And once you had an equation, you could manipulate it with algebra. You could calculate things about the curve without ever drawing it. You could turn geometry, which had always been visual and spatial, into something abstract and symbolic. This was the bridge. This was the thing that made calculus possible. Because once you could describe a curve with an equation, you could start asking algebraic questions about it. Questions like, what's the slope of this curve at a particular point? How fast is it changing? What's the area underneath it? And those questions, those exact questions, are what calculus answers. But to see how those questions got answered, we need to talk about a generation of mathematicians who came right after Descartes, people like Pierre de Fermat and Blaise Pascal and Bonaventura Cavalieri, each of whom grabbed a different piece of the puzzle and pushed it a little further toward the edge of something extraordinary. Let's start with Cavalieri, because his idea is one of those things that sounds almost too simple to be important, but it cracked open a door that had been stuck for centuries. Bonaventura Cavalieri was an Italian Jesuit, a mathematician working in Bologna in the early 1600s, and he had this principle, we call it Cavalieri's principle, that went something like this. Imagine you have two solids, let's say 2 loaves of bread, sitting side by side on a table. Now imagine you take a knife and slice through both of them at every possible height. If, at every single height, the cross-sectional area of one loaf exactly equals the cross-sectional area of the other loaf, then the 2 loaves must have the same volume. That's it. That's the whole principle. And you might be thinking, well, yeah, obviously. But here's what's sneaky about it. Cavalieri was saying that you could think of a solid object as being made up of infinitely many, infinitely thin slices, like a deck of cards with infinitely many cards, each one infinitely thin. And if you could figure out the area of each slice, you could, in some sense, stack them all up and get the volume. This was dangerous territory, philosophically, because he was playing with infinity. He was saying, let me chop this thing into infinitely many pieces and reason about them. And a lot of mathematicians at the time were deeply uncomfortable with that. They'd inherited the Greek anxiety about infinity, that old worry that if you start dividing things infinitely, you end up with paradoxes and contradictions. But Cavalieri pushed ahead anyway, and his method worked. It gave correct answers. You could use it to find volumes of all sorts of shapes, cones, spheres, paraboloids, things that had been incredibly difficult with classical methods. He published his results in 1635 in a book called Geometria Indivisibilibus, Geometry by Indivisibles. And even though the logical foundations were shaky, even though nobody could quite explain why it was okay to treat a solid as infinitely many slices, the results were undeniably right. And that tension between a method that works beautifully and a method that nobody can fully justify, that tension is going to hang over mathematics for the next 200 years. Keep that in the back of your mind, because we'll come back to it. Now, Pierre de Fermat. You probably know the name from Fermat's last theorem, that famous problem he scribbled in the margin of a book, claiming he had a proof that was too large to fit. That problem took over 300 years to solve, and Andrew Wiles finally cracked it in 1995. But Fermat did something else, something arguably more important for the story we're telling, and it gets far less attention. Fermat figured out how to find the maximum and minimum values of a curve. And the way he did it was breathtakingly close to what we now call taking a derivative. Here's what he did. Say you have a curve described by some equation. Thanks to Descartes, you can do that now, and you want to find the point where the curve reaches its highest value. Fermat's insight was this. At a maximum point, the curve is, for just a moment, flat. It's not going up anymore, and it hasn't started going down yet. It's level. The slope is 0. So he developed a technique where he would take the equation of the curve, shift the input by a tiny amount, he called it e, just a small quantity, and then set the original value equal to the shifted value. Because at a maximum, the function's value barely changes when you nudge the input a tiny bit. Then he'd do some algebra, divide through by e, and then, and this is the part that made people nervous, he'd set e equal to 0. Just let it vanish, and out would pop the exact location of the maximum. If that sounds like a derivative to you, you're absolutely right. Fermat was essentially computing what we'd now write as f prime of x equals 0, finding where the derivative is 0 to locate maxima and minima. He just didn't have the formal framework to call it that. He didn't have the concept of a limit. He had this slightly magical step where e was small but not 0, and then suddenly it was 0, and everyone kind of squinted at it and said, wait, can you do that? Is that legal? And Fermat more or less shrugged and said, look, it gives the right answers. Which it did. Every time. This was happening in the 1630s and 1640s in France, and Fermat was doing it mostly in letters to friends and colleagues. He wasn't a professional mathematician. He was a lawyer, a magistrate in Toulouse. Mathematics was his passion, his hobby, the thing he did after his day job. And yet this lawyer in southern France was, in his spare time, inventing one of the two fundamental operations of calculus. He just didn't know that's what he was doing. And then there's Blaise Pascal, Pascal is one of those figures who makes you feel a little inadequate because he accomplished an absurd amount in a tragically short life. He died at 39. By the time he was 16, he'd written a significant treatise on conic sections. He invented one of the first mechanical calculators, an actual physical machine that could add and subtract to help his father with tax calculations. He made important contributions to probability theory, to fluid mechanics, to philosophy. And for our story, what matters is his work on what he called the arithmetic triangle, what we now call Pascal's triangle. You've probably seen it. It's that triangular arrangement of numbers where each number is the sum of the two numbers above it, one at the top, then 1, 1, then 1, 2, 1, then 1, 3, 3, 1, and so on. It looks like a simple pattern, a curiosity, but Pascal showed that this triangle encodes an enormous amount of mathematical information. It tells you the coefficients you get when you expand expressions like x plus y raised to some power. It connects to probability. If you flip a coin 10 times, Pascal's triangle tells you how many ways you can get exactly 3 heads. And here's where it touches our story. Pascal used the triangle and the patterns within it to compute areas under curves. Specifically, he worked on the curve called the cycloid, the path traced by a point on the rim of a rolling wheel. And he used summation techniques that were, in essence, integration. He was adding up infinitely many infinitely small pieces to find areas and volumes, just like Cavalieri, but with more algebraic sophistication. There's actually a wonderful story about Pascal and the cycloid. By the late 1650s, Pascal had undergone a profound religious conversion and had largely given up mathematics, devoting himself to theology and his famous philosophical work, the Pensées. But one night, and this is supposedly a true story, he was suffering from a terrible toothache, and to distract himself from the pain, he started thinking about the cycloid. And as he thought about it, the toothache went away. Pascal took this as a sign from God that it was okay for him to do mathematics, at least about this particular curve. So he threw himself into the problem, solved several deep questions about the cycloid's area and the volumes of solids generated by rotating it, and then issued a public challenge to other mathematicians to match his results. It's a beautiful little moment. This deeply religious man, in pain in the middle of the night, finding relief in the pure abstraction of a rolling wheel, tracing a curve through space. So by the middle of the 17th century, you have all these pieces lying on the table. Cavalieri's indivisibles, the idea that you can slice shapes infinitely thin and add them up. Fermat's method of finding maxima and minima, essentially differentiation without the name. Pascal's summation techniques and his work connecting algebra to geometric areas. Descartes' coordinate system tying equations to curves. And further back, Archimedes' method of exhaustion, the Kerala school's infinite series, Ibn al-Haytham's early integration. All of these are fragments of calculus. Each one is a glimpse of the whole picture from a different angle, but nobody has put them together yet. Nobody has looked at all of these techniques and said, wait, these are all part of the same thing. The operation of finding slopes and the operation of finding areas, those aren't just two separate tricks. They're inverses of each other. They're connected in a deep, fundamental way. That connection, that revelation, is what we call the fundamental theorem of calculus. And it's arguably the single most important insight in the history of mathematics. And to understand it, let's slow down for a moment and think about what it actually says. Because it's one of those things that sounds technical, but is actually profoundly intuitive once you see it. Think about driving a car. You're on a highway, and your speedometer tells you how fast you're going at every moment. That's a rate of change. Your speed is the rate at which your position is changing. Now, if I asked you how far you've traveled in the last hour, what would you do? You'd look at your speed over that hour and somehow accumulate it. If you were going a steady 60 miles per hour, easy, 60 miles. But if your speed was varying, speeding up, slowing down, you'd need to add up all those little bits of distance, moment by moment, across the whole hour. You'd need to, in some sense, sum up the speed over time. Here's the thing. Speed is the derivative of position. It tells you how position changes, and distance traveled is the integral of speed. It's the accumulation of speed over time. So the derivative and the integral are reverse operations. If you differentiate position, you get speed. If you integrate speed, you get back position. They undo each other, like multiplication and division, like squaring and taking a square root. And that relationship, that beautiful symmetry, is the fundamental theorem of calculus. Nobody before the 1660s had clearly seen this. People were finding slopes over here and areas over there, using completely different methods, thinking of them as completely different problems. And then two men, working more or less independently in two different countries, saw the connection. And in seeing it, they unified all those scattered fragments into a single coherent system. They invented calculus. Their names were Isaac Newton and Gottfried Wilhelm Leibniz. And the story of how they each arrived at this insight and the bitter, ugly, decades-long fight over who deserved credit for it. That story is one of the most dramatic episodes in the history of science. Let's start with Newton, because his path to calculus is tangled up with one of the most extraordinary bursts of intellectual creativity any human being has ever experienced. In 1665, Isaac Newton was 22 years old, a student at Trinity College, Cambridge, quiet, solitary, not particularly distinguished. And then the plague came to England. The Great Plague swept through London and into the countryside, and Cambridge University shut down. Students were sent home. Newton went back to his family's farm in Woolsthorpe, a small village in Lincolnshire, and for roughly 18 months, with almost no one to talk to, no library to speak of, no colleagues, no mentors, he sat alone and thought about the world. And what came out of that solitary thinking was staggering. In those 18 months at Woolsthorpe, Newton didn't just work on one problem. He made foundational contributions to optics, figuring out that white light is actually a mixture of all the colors of the spectrum. He began developing his theory of gravity. Yes, the apple story probably has some kernel of truth, though the details have been romanticized over the centuries, and he developed what he called his method of fluxions, which is what we now call calculus. Think about that for a second. A 22-year-old, sitting alone on a farm during a plague, essentially invents three major branches of science and mathematics in a year and a half. There's really nothing else like it in the history of human thought. Maybe the closest comparison is Einstein's miracle year of 1905. But even Einstein was working at the patent office, surrounded by a city, corresponding with friends. Newton was alone in the countryside with his notebooks. So what exactly did Newton figure out? Let's talk about that. Newton was thinking about change, about things that move, things that grow, things that flow. That's actually where his terminology came from. He called changing quantities fluents, things that flow, and their rates of change he called fluxions. If you have a quantity that's changing over time, say the position of a falling apple, the fluent is the position, and the fluxion is the velocity, the rate at which that position is changing. And he developed systematic rules for finding fluxions from fluents and fluents from fluxions. In modern language, he developed rules for differentiation and integration. Here's what's really clever about Newton's approach. He thought of everything in terms of motion and time. Every variable was something that was flowing, changing, moving through moments. Even purely abstract mathematical quantities, like the coordinates of a point on a curve, he imagined as being generated by motion. A curve wasn't just a static shape sitting there on a page. It was the path traced out by a moving point. And if you think of it that way, then the slope of the curve at any instant is just the velocity of that point at that instant. The geometric problem of finding a tangent line becomes a physics problem of finding a velocity. And Newton was a physicist at heart, so this way of thinking came naturally to him. He used something he called an infinitely small increment of time. He denoted it with a little letter O. If a quantity x is flowing, then after an infinitely small moment, O, the quantity becomes x plus its fluxion times O. And then he could work out how other quantities that depend on x change in that same moment, expand everything out. And then, and this is the crucial move, discard all the terms that still have O in them, because O is infinitely small, so those terms vanish. What's left is the rate of change. Now, if that sounds familiar, it should. It's essentially the same trick Fermat was using with his mysterious quantity E back in the 1630s. Set up the expression, let E get small. Throw away the leftover E terms. Newton's version was more systematic, more general, more powerful. He could handle far more complicated expressions. He could chain operations together. He could work with curves and equations that would have been completely out of Fermat's reach. But the underlying logic had that same slightly shaky quality. You're treating O as a real number when you divide by it, and then treating it as zero when you throw it away. Which is it? Is it something or is it nothing? Newton was aware of this problem. He wasn't comfortable with it. Over the years, he actually tried several different approaches to put his method on firmer logical ground. At one point, he tried using ratios of vanishing quantities, what he called first and last ratios, which is actually pretty close to the modern concept of a limit. The idea being that you're not saying O equals zero. You're looking at the ratio of two quantities as they both approach zero simultaneously and asking what that ratio approaches. That's subtle, and it's essentially the right idea, but Newton never quite pinned it down with the precision that would satisfy a modern mathematician. That wouldn't happen for another century and a half, but we'll get to that. The important thing is what Newton could do with his method, and what he could do was extraordinary. He could find tangent lines to virtually any curve. He could find areas under curves. He could find the maximum and minimum values of functions. He could solve what we now call differential equations, equations that relate a quantity to its own rate of change. And he could do all of this systematically, with algorithms, with rules you could follow step by step. It wasn't a collection of clever tricks anymore. It was a machine. You feed in a problem, you turn the crank, and the answer comes out. And here's where the fundamental theorem really shows its power. Before Newton, if you wanted to find the area under some curve, you had to do it from scratch every time. Set up an approximation with thin rectangles or triangles, sum them up, take a limit. Archimedes style work, painstaking and specific to each problem. But Newton realized that if you could find an antiderivative, a function whose derivative gives you the curve you're interested in, then you could just evaluate that antiderivative at 2 points and subtract. Finding areas became almost trivial, as long as you could find antiderivatives. And Newton was very, very good at finding antiderivatives. He developed power series expansions, infinite series representations of functions that let him integrate things that nobody had been able to integrate before. He was building on the work of people like Madhava, though he almost certainly didn't know about the Kerala school's results. He was rediscovering and extending those ideas independently. But here's the thing about Newton, and this is crucial for understanding the drama that's about to unfold. He didn't publish any of this, not right away, not for years, not for decades. Newton was famously secretive, almost pathologically so. He had a deep fear of criticism, of public dispute, of having his ideas attacked. He wrote up his results in private manuscripts, shared them with a small circle of colleagues, and sat on them. His main treatise on calculus, which he called De Methodis Serierum et Fluxionum, on the methods of series and fluxions, was written in 1671. It wasn't published until 1736, 9 years after his death. Let that sink in. He had the most powerful mathematical tool the world had ever seen, and he kept it essentially private for most of his life. Meanwhile, on the continent, Gottfried Wilhelm Leibniz was walking a very different path to the same destination. Leibniz was, in almost every way, Newton's opposite in temperament. Where Newton was solitary and secretive, Leibniz was sociable and prolific. Where Newton was a focused, obsessive thinker who bored into problems with terrifying intensity, Leibniz was a polymath who scattered his attention across philosophy, logic, theology, diplomacy, law, linguistics, and mathematics. He was born in Leipzig in 1646, 4 years after Newton, and he came to serious mathematics relatively late. He was in his late 20s before he really engaged with the cutting-edge work being done in Europe. In 1672, Leibniz went to Paris on a diplomatic mission, and that trip changed his life. Paris was the intellectual center of Europe, and Leibniz threw himself into its mathematical community. He met Christian Huygens, the great Dutch physicist and mathematician, who became something of a mentor. Huygens gave Leibniz reading lists, posed problems to him, pushed him to develop his mathematical skills. And Leibniz, who was brilliant and a fast learner, absorbed everything he could. He studied Pascal's work on summation and areas. He studied Descartes' geometry. He read about Cavalieri's indivisibles. And over the next few years, working intensely, he developed his own version of calculus. Leibniz's approach was different from Newton's in flavor, though it arrived at the same truths. Where Newton thought in terms of motion and time, fluence and fluxions, Leibniz thought in terms of sums and differences. He was deeply influenced by Pascal's work on numerical sequences, where you could take a sequence of numbers, form the differences between consecutive terms, and then sum those differences to get back to the original sequence. Leibniz saw that the relationship between areas and tangent slopes was the continuous version of this same pattern. Differences correspond to derivatives, sums correspond to integrals, and they undo each other. And here's where Leibniz made his most lasting contribution, not necessarily in the theorems he proved, but in the language he invented to express them. Leibniz was obsessed with notation. He believed that the right symbols could make thinking easier, could make patterns visible, could practically do the reasoning for you. And the notation he created for calculus was gorgeous. He introduced the elongated S symbol, the integral sign, which stands for summa, the Latin word for sum, because integration is a kind of continuous summation. He introduced the notation dy over dx for the derivative, suggesting a tiny change in y divided by a tiny change in x. he introduced the letter D itself to mean an infinitesimally small difference. And this notation caught on. It caught on because it was good. Really, really good. It was intuitive. It was suggestive. It practically told you how to manipulate the expressions. When you write dy over dx, it looks like a fraction, and in many situations you can manipulate it like a fraction, and it gives you the right answer. When you write the integral sign followed by f of x dx, the dx reminds you that you're summing up infinitely many, infinitely thin slices, each with width dx. The notation encodes the meaning. Newton's notation, by contrast, dots over letters for fluxions, complicated expressions for fluents, was clunkier, harder to work with, harder to extend. Leibniz published his first paper on calculus in 1684 in a journal called the Acta Eruditorum. It was dense, it was hard to follow, it was only a few pages long, and it contained almost no proofs. But it was published. It was out there, in print, with a date on it. And then in 1686, he published a paper on integral calculus, and the mathematical community on the continent, the Bernoulli brothers in Switzerland, L'Hôpital in France, others, picked up Leibniz's methods, learned his notation, and started using calculus to solve problems at a tremendous rate. A whole school of Leibnizian calculus developed on the continent, pushing the subject forward, applying it to physics, to geometry, to mechanics. And Newton watched this happening from England, and he seethed, because he had done it first. He knew he had done it first. His private manuscripts predated Leibniz's publications by more than a decade. And now, here was this German philosopher getting credit for inventing calculus, using notation that was spreading across Europe, building a following of disciples, and Newton's own contributions were languishing in unpublished manuscripts that only a handful of people had ever seen. The question that poisoned the relationship between these two men, and that split the mathematical world into warring camps for the better part of 50 years, was simple and brutal. Did Leibniz steal Newton's ideas? Did he see Newton's unpublished manuscripts during a visit to London in 1676, absorb the key insights, and then dress them up in his own notation and publish them as his own? Or did he develop calculus genuinely independently, arriving at the same truths by a different path, as has happened many times in the history of mathematics and science? The honest answer, as best as historians can reconstruct it, is that Leibniz almost certainly developed his calculus independently. There was some limited correspondence between Newton and Leibniz in 1676, through intermediaries, in which Newton hinted at his results without revealing his methods. He actually encoded some of his key findings as anagrams, scrambled Latin sentences that could be decoded later to establish priority, but that conveyed no actual information. Leibniz may have seen some of Newton's manuscripts briefly during his London visit, but the evidence suggests he didn't understand them at the time, and his own approach was different enough in its foundations and its notation that independent invention is the most plausible explanation. But Newton didn't see it that way. And as the years went on, the dispute escalated from private grumbling to public accusation to institutional warfare. Newton, who by the early 1700s was the most powerful scientist in England, president of the Royal Society, knighted by the Queen, master of the Royal Mint, used his institutional power to wage a campaign against Leibniz. In 1712, the Royal Society convened a committee to investigate the priority dispute, and Newton secretly wrote the committee's report himself. The report, unsurprisingly, found in Newton's favor and essentially accused Leibniz of plagiarism. Leibniz, by this point, an aging man in declining health, was devastated. He spent his last years defending himself, writing letters, appealing to anyone who would listen. He died in 1716, largely alone. His employer, the Elector of Hanover, who had by then become King George I of England, didn't even attend his funeral. It was a bitter, ugly end for a man who had made one of the greatest intellectual contributions in human history. And the tragedy of the dispute goes beyond the personal. It had real consequences for mathematics. Because English mathematicians loyal to Newton refused to adopt Leibniz's superior notation. They stuck with Newton's dots and cumbersome expressions for over a century, while continental mathematicians, using Leibniz's elegant di over dx notation, raced ahead. The great advances in calculus and mathematical physics in the 18th century, the work of Euler, of Lagrange, of Laplace, happened almost entirely on the continent. English mathematics stagnated, falling behind for generations. National pride and personal bitterness held back an entire country's scientific progress. It wasn't until the early 19th century that a group of Cambridge students, half-jokingly calling themselves the Analytical Society, campaigned to adopt Leibnizian notation in England, and even then, it was a hard-fought battle. Charles Babbage, John Herschel, George Peacock. These were young men, undergraduates really, and they had the audacity to look at the way mathematics was being taught at Cambridge and say, "This is absurd. We're clinging to Newton's notation out of patriotism, not logic." Babbage, who you might know better for his later work designing mechanical computers, had a real flair for provocation. He described the Society's mission as promoting the principles of pure deism as opposed to the dot age of the university. Deism, as in Leibniz's D notation. Dot age, as in Newton's dots over variables, and also, dotage, meaning senility. It was a pun. A pretty good one, honestly. And the thing is, they were right. Not just stylistically right, but practically right. Leibniz's notation wasn't just prettier. It was functionally superior for the kind of work mathematicians needed to do. When you write dy over dx, you can manipulate it almost like a fraction. You can separate the differentials, rearrange them, chain them together. It practically invites you to see relationships between variables. Newton's dot notation, where you put a dot over x to mean the rate of change of x, works fine for simple cases, but it becomes clumsy fast. Try writing a second derivative in Newton's notation versus Leibniz's. In Leibniz's, you write d squared y over dx squared. It's clear, it's compact, and it generalizes beautifully. Newton's version requires stacking dots or inventing new conventions for every new situation. And when you get into partial derivatives, functions of multiple variables, the chain rule applied across nested functions. Leibniz's framework just handles it more gracefully. So by the 1820s and 1830s, Cambridge was finally making the switch. And it mattered. It mattered because once English mathematicians started speaking the same symbolic language as their continental counterparts, they could finally participate in the conversation again. They could read Euler, read Lagrange, read Laplace, and build on that work instead of constantly translating between incompatible notations. It's a small reminder that notation isn't just cosmetic. The symbols you use shape the thoughts you can think. A good notation is a thinking tool. A bad one is a thinking trap. But let's go back now, because while England was stuck in its dot age, incredible things were happening on the continent throughout the 1700s. And the person at the center of almost all of it, the person who took the raw, powerful, slightly messy calculus that Newton and Leibniz had created and turned it into a vast, systematic, breathtakingly productive mathematical framework, was Leonhard Euler. If Newton and Leibniz invented calculus, Euler is the one who showed the world what it could actually do. Euler was born in Basel, Switzerland, in 1707. His father was a pastor who had studied mathematics under Jacob Bernoulli, one of the Bernoulli brothers who had been among the first to master Leibniz's calculus. So Euler grew up in a household where mathematics was in the air. He studied under Johann Bernoulli, Jacob's younger brother, who was arguably the finest mathematician in Europe at the time. Johann recognized Euler's talent immediately. The kid was extraordinary. By his late teens, Euler was already publishing original mathematical work. By his 20s, he was one of the most productive mathematicians alive. And he just never stopped. Here's something that gives you a sense of the scale of Euler's output. The complete collection of his published works, which scholars have been compiling since the early 20th century, runs to over 80 volumes. 80. He wrote on calculus, number theory, mechanics, optics, astronomy, music theory, fluid dynamics, cartography. There was almost no branch of mathematics or mathematical physics he didn't touch, and in most of them, he made foundational contributions. He averaged about 800 pages of new mathematics per year for most of his career. And here's the part that always gets me. He went blind. In his late 50s, he lost the sight in his remaining eye. He'd already lost one eye years earlier. So for the last 17 years of his life, Euler was completely blind, and his productivity actually increased. He had an astonishing memory and could do enormous calculations in his head. He dictated papers to assistants. He once settled an argument between two students who had gotten different answers on a complicated infinite series calculation by doing the entire computation mentally. Now, what did Euler actually do for calculus? Almost everything is the short answer. He's the one who standardized the notation we still use today, the function notation f of x. That's Euler. The number e, the base of the natural logarithm. Euler didn't discover it, but he named it, calculated it to extraordinary precision, and revealed its deep connections to other parts of mathematics. The use of pi for the ratio of a circle's circumference to its diameter. That became standard largely because Euler used it consistently. The imaginary unit I for the square root of -1, Euler. Sigma notation for sums, Euler. He's the one who wrote down what many mathematicians consider the most beautiful equation in all of mathematics, e to the power of I minus pi plus 1 equals 0. 5 fundamental constants, e, I, pi, 1, and 0, linked in a single, compact, almost impossibly elegant relationship. That's Euler's identity, and it falls directly out of the calculus of complex exponentials that he developed. But beyond notation, Euler transformed calculus from a collection of clever techniques into a systematic discipline. He wrote textbooks, his Introductio in Analysin Infinitorum in 1748, his Institutiones Calculi Differentialis in 1755, and his 3-volume Institutiones Calculi Integralis, completed in 1770, that organized and extended the subject so thoroughly that they became the standard references for generations. He developed methods for solving differential equations that engineers still use today. He worked out the calculus of variations, which asks not just for the value that optimizes a function, but for the entire curve or path that optimizes some quantity. Think about that. Instead of finding the single number that makes something biggest or smallest, you're finding the whole shape, the whole trajectory. What curve between 2 points has the shortest travel time for a ball rolling under gravity? That's the Brachistochrone problem, which Johann Bernoulli had posed as a challenge back in 1696, and it's the kind of question the calculus of variations was built to answer. And Euler applied calculus to physics with a relentlessness that transformed both fields. He wrote down the equations governing the motion of rigid bodies, the way a spinning top wobbles, the way a thrown object tumbles through the air. He developed the equations of fluid dynamics that bear his name, the Euler equations, which describe how an idealized fluid flows. These aren't toy equations. Modified and extended, they're the ancestors of the Navier-Stokes equations that engineers use today to design airplane wings, predict weather patterns, model ocean currents. Every time you fly in a plane, the shape of that wing was optimized using computational tools whose mathematical foundations trace back to Euler, sitting in St. Petersburg or Berlin, scratching away with a quill pen, or later, dictating from memory in total darkness. Euler wasn't working alone, of course. The 18th century was a golden age for mathematical physics on the continent, and several brilliant figures were extending calculus in different directions. Jean-Laurent d'Alembert in France worked on the wave equation, the differential equation that describes how a vibrating string moves, how sound propagates, how waves travel through any medium. D'Alembert and Euler actually had a famous disagreement about what kinds of functions could be solutions to the wave equation, a dispute that wouldn't be fully resolved for another century, and that pushed mathematicians to think much more carefully about what a function actually is. Then there was Joseph Louis Lagrange, born in Turin in 1736, who took the calculus of variations and gave it a more algebraic, more abstract formulation. Lagrange wanted to strip calculus of all its geometric and physical intuition and reduce it to pure algebra. He actually tried to rebuild calculus entirely on the basis of Taylor series, representing every function as an infinite polynomial and defining derivatives as the coefficients of those series, without any reference to limits or infinitesimals at all. It was an ambitious program, and ultimately it didn't quite work. There are functions that don't behave nicely as Taylor series, and Lagrange's approach couldn't handle them. But his instinct, that calculus needed a more rigorous algebraic foundation, was absolutely right. And his reformulation of mechanics, what we now call Lagrangian mechanics, used calculus in a way that was so elegant and so powerful that it became one of the pillars of theoretical physics. When physicists today work on quantum field theory or general relativity, they're often working in a Lagrangian framework. The mathematics of the most fundamental physics we know rests on a reformulation of calculus that a man from Turin devised in the 1780s. And then there was Pierre-Simon Laplace, who used calculus to tackle celestial mechanics, the motion of planets, moons, and comets, with a thoroughness that went far beyond even Newton. Laplace's 5-volume Mécanique Céleste, published between 1799 and 1825, was an attempt to account for every known irregularity in the solar system using calculus and Newtonian gravity. And he largely succeeded. Where Newton had worried that the solar system might be unstable, that small gravitational perturbations between planets might accumulate over time and eventually send everything flying apart, Laplace showed, or at least argued convincingly, that the system was self-correcting. The perturbations were periodic. They'd push things one way for a while, then push them back. The solar system was stable. When Napoleon supposedly asked Laplace where God fit into his system, Laplace is said to have replied, "I had no need of that hypothesis." Whether or not the exchange actually happened exactly that way, it captures something true about what calculus had made possible. You could explain the machinery of the heavens with differential equations. You didn't need miracles to account for planetary motion. You needed mathematics. But here's the thing that was quietly bothering people throughout all of this extraordinary progress. For all its power, for all the problems it could solve, calculus still didn't have a solid logical foundation. The basic operation, taking a ratio of infinitely small quantities, or letting something approach zero but not actually be zero, or summing up infinitely many infinitely thin slices, none of it had been made rigorous. Euler used infinitesimals freely, treating them as quantities that were simultaneously zero and not zero, and he got correct answers because his intuition was superb. But the logical ground underneath was shaky, and people noticed. The most famous critic was the Irish philosopher Bishop George Berkeley, who in 1734 published a devastating little pamphlet called The Analyst. Berkeley wasn't a mathematician, he was a theologian, actually. But he had a sharp, logical mind, and he zeroed in on exactly the weak point. When Newton or Leibniz computed a derivative, they divided by an increment, call it h or o or dx, and then, at the end, they set that increment equal to zero. But you can't divide by something and then say it's zero. If it's zero, you just divided by zero, which is meaningless. If it's not zero, then your answer is only approximate, not exact. Berkeley called these infinitesimals the ghosts of departed quantities, which is one of the great trash talk lines in the history of ideas. And he had a point. The calculus worked. Nobody disputed that. But nobody could explain why it worked without hand-waving at some crucial step. This bothered mathematicians more and more as the 18th century wore on. And the resolution, when it finally came, would transform not just calculus, but the entire nature of mathematical reasoning. It started with a quiet, methodical French professor named Augustin Louis Cauchy, working in Paris in the 1820s, and it would be completed by a German schoolteacher named Karl Weierstrass a few decades later. Between them, they would replace the vague, intuitive notion of approaching with something precise, something bulletproof, something that could withstand any logical attack. They would invent the concept of the limit, not as a hand wave, but as a rigorous definition built on inequalities and logic. And the way they did it is actually one of the most beautiful things in all of mathematics. So let's slow down and really walk through it. Cauchy arrived at the École Polytechnique in Paris around 1815 as a young professor, and he was a peculiar character. Deeply religious, politically conservative, not especially popular with his students, who found his lectures demanding and his personality a bit cold. But the man had an almost obsessive need for precision. Where Euler would cheerfully manipulate infinite series and trust that things would work out, Cauchy wanted to know exactly why each step was valid. And he started from the very beginning, from the concept that underpins everything else in calculus, the limit. Now, people had used the word limit before Cauchy. Newton himself talked about quantities approaching limits. But what did approaching actually mean? If I say a sequence of numbers approaches some value L, what am I really claiming? That the numbers get close to L. How close? Close enough? Close enough for what? You can see the problem. It's all fuzzy. And fuzzy is exactly what Berkeley had attacked. Here's what Cauchy did, and it's so simple once you see it that you almost can't believe it took 2,000 years to get here. He said, a sequence approaches a limit L if, For any degree of closeness you care to name, any tolerance, any margin of error, no matter how tiny, eventually, the terms of the sequence all fall within that margin. That's it. You pick the tolerance. I show you that the sequence eventually stays inside it. You pick a smaller tolerance. I show you it still works. You pick an absurdly, microscopically small tolerance. I show you it still works. If I can always win that game, no matter what tolerance you throw at me, then the sequence converges to L period. Think about what that does. It completely eliminates the need to talk about infinitesimals, about quantities that are somehow both zero and not zero. You never have to say infinitely close or vanishingly small. Instead, you talk about specific, finite numbers. Your tolerance is some concrete positive number, like 1/10 or 1/1,000,000th or 1/1,000,000,000th, and you prove that the sequence eventually stays within that distance of the limit. Everything is finite. Everything is nailed down. There are no ghosts of departed quantities anywhere in sight. Cauchy published this framework in his textbooks starting in the 1820s, his Cours d'analyse in 1821, and his Résumé des leçons in 1823. And he didn't just define limits, he rebuilt calculus on top of them. Continuity, for instance. What does it mean for a function to be continuous? Intuitively, you might say it means you can draw the graph without lifting your pen, but that's a visual metaphor, not a definition. Cauchy defined it precisely. A function is continuous at a point if, when the input changes by a small amount, the output also changes by a small amount. And small here means the same game. For any tolerance on the output, there's a corresponding tolerance on the input that guarantees you stay within bounds. Derivatives, integrals, convergence of series. Cauchy recast all of them in terms of this same logical structure. But here's the thing. Cauchy's definitions, as groundbreaking as they were, still had a slightly informal flavor. He would say things like approaches indefinitely, or as small as one wishes in prose, and sometimes his arguments had gaps. He was pointing in exactly the right direction, but the final, fully symbolic formulation, the one you'd encounter in a modern analysis textbook, that came from Karl Weierstrass. Weierstrass is one of those figures whose life story is almost comically unlikely for someone who'd become the most important analyst of the 19th century. He was born in 1815 in Westphalia, and his father pushed him to study law and commerce at the University of Bonn. Weierstrass apparently spent much of his time there, drinking beer and fencing. He was reportedly quite good at fencing, and he left without a degree. He then trained as a secondary school teacher and spent over a decade teaching math, German, geography, even gymnastics at small-town schools in Prussia. For years, this man who would reshape the foundations of mathematics was grading homework from teenagers in rural Germany. But the whole time, in his spare hours, he was doing research. Serious, deep, original research on complex analysis and the theory of functions. In 1854, when he was nearly 40, he published a paper on abelian functions that was so stunningly brilliant that the mathematical world basically did a collective double-take. Within 2 years, he had an honorary doctorate and a professorship at the University of Berlin, where he would spend the rest of his career. And it was at Berlin that Weierstrass conducted his famous lectures on analysis, lectures that drew students from across Europe and shaped an entire generation of mathematicians. In those lectures, he took Cauchy's ideas and made them completely, unambiguously precise. This is where the epsilon-delta definition crystallizes into its final form. You've probably heard those Greek letters before if you've taken any calculus course. Epsilon, the small Greek letter epsilon, represents the tolerance on the output, how close you want the function to be to the limit. Delta, the small Greek letter delta, represents the corresponding tolerance on the input. The definition says, for every epsilon greater than 0, there exists a delta greater than 0, such that whenever the input is within delta of the target point, the output is within epsilon of the limit. Now, I know that sounds abstract. Let me try to make it feel more concrete. Imagine you're an archer and you're trying to hit closer and closer to the bullseye on a target. Someone challenges you. Can you land your arrow within 1 inch of center? You say sure, and you stand at a certain distance and do it. Then they say, okay, can you land within ½ an inch? You step a little closer, adjust your aim, and you do it. 1/4 inch? 1/8? 100th? If, for every possible challenge, every margin of error around the bullseye, no matter how tiny, you can always find a distance to stand at and a technique that guarantees you'll land within that margin, then we say your shooting converges to the bullseye. That's the epsilon-delta idea. Epsilon is the size of the ring around the bullseye. Delta is the adjustment you make to guarantee you hit inside it. What Weierstrass did was insist that every theorem in calculus be provable using only this kind of reasoning. No appeals to geometric intuition, no vague talk of motion or flowing quantities, just pure logical statements about numbers and inequalities. This program is sometimes called the arithmetization of analysis, and it was a massive philosophical shift. Calculus had been born from physics, from thinking about moving objects and changing quantities. Now it was being rebuilt as a branch of pure logic, standing on its own feet, independent of any physical interpretation. And this wasn't just pedantry. It mattered, because as mathematicians pushed into more exotic territory, intuition started to fail them. Weierstrass himself demonstrated this dramatically. In 1872, he presented a function that is continuous everywhere, meaning it has no jumps, no breaks. You could draw it without lifting your pen, but is differentiable nowhere. Nowhere. At every single point, the function has no well-defined slope. It's continuous, but infinitely jagged, like a fractal before fractals had a name. This was shocking. Most mathematicians had assumed that a continuous function had to be smooth, or at least smooth almost everywhere. Weierstrass showed that assumption was completely wrong, and you could only discover something like that and prove it rigorously if you had precise definitions to work with. Intuition alone would never have found it. Intuition actually pointed in the wrong direction. This is a pattern you see again and again in the history of mathematics, and it's worth sitting with for a moment. The tools that seem overly formal, overly fussy, the definitions that make students groan and ask, why do we need all this rigor? Those tools exist because, at some point, someone's intuition led them astray, and the only way to catch the error was to be painfully precise. The epsilon-delta framework isn't there to make your life harder. It's there because without it, you can prove things that are false. So by the second half of the 19th century, calculus finally had a solid logical foundation. But the story doesn't stop there, because the rigorization program kept going deeper. If calculus is built on limits, and limits are defined in terms of real numbers, then what exactly are real numbers? This sounds like a silly question. You know what real numbers are. They're just numbers on the number line, right? But what is the number line? What guarantees that it has no gaps? Why should the square root of 2 actually exist as a definite point? These questions led to yet another foundational crisis and yet another round of brilliant work. In 1858, the German mathematician Richard Dedekind was teaching calculus at the Polytechnic in Zurich, and he realized he was relying on geometric intuition about the number line that he couldn't actually prove. So he set about constructing the real numbers from scratch, using only rational numbers, fractions, and pure logic. His method, published in 1872, the same year Weierstrass unveiled his everywhere continuous, nowhere differentiable function, used what he called Schnitte, cuts. A Dedekind cut is a way of slicing all the rational numbers into two groups, everything below a certain value and everything above it. And the cut itself defines a real number. Even if that real number is irrational, like the square root of 2, the cut pins it down precisely as the boundary between rationals that are too small and rationals that are too large. Around the same time, Georg Cantor, who had been a student of Weierstrass in Berlin, was developing his own construction of the real numbers using Cauchy sequences, which are sequences of rational numbers that get closer and closer together and thus should converge to something. Both approaches worked. Both gave you the complete real number line with no gaps, and both revealed something profound, the continuum, that smooth, unbroken line that seems so simple and obvious, is actually an incredibly rich and subtle mathematical object. Cantor would go on to show that the real numbers are uncountably infinite. There are, in a precise sense, more real numbers than there are fractions, more points on a line segment than there are whole numbers. This discovery opened the door to set theory, to the study of different sizes of infinity, and eventually to the logical foundations of all of mathematics. But let's not lose the thread here, because what matters for our story is what all this rigor made possible. Once you had a bulletproof definition of limits, a solid construction of the real numbers, and precise definitions of continuity, derivatives, and integrals, you could start asking questions that would have been meaningless before. Questions like, exactly which functions can be integrated? What does it mean for an infinite series of functions to converge? Can you interchange limits and integrals? These aren't abstract puzzles. They come up constantly in physics and engineering. Every time you try to solve a differential equation by writing the solution as an infinite series, which is basically all the time. And this is where the story takes another fascinating turn, because the question of which functions can be integrated led directly to one of the most important generalizations in the history of calculus. Bernhard Riemann, another student connected to the Göttingen tradition, a shy, deeply creative mathematician who died tragically young at 39, formalized the integral in the 1850s in a way that went well beyond what Cauchy had done. Riemann's integral, which is essentially the version you learn in a standard calculus course today, works by chopping up the area under a curve into thin rectangles, adding up their areas, and taking a limit as the rectangles get thinner and thinner. But Riemann was precise about exactly when this process works and when it doesn't. He showed that some functions are too wild, too discontinuous to be integrated by his method, and that raised the obvious question. Could you build a better integral, one that could handle more functions? The answer came from Henri Lebesgue, a French mathematician working at the turn of the 20th century, and his approach was so clever, so fundamentally different in its philosophy, that it's worth taking a moment to really appreciate what he did. So picture Riemann's approach one more time. You've got a function, some curve drawn across a graph, and you want to find the area underneath it. Riemann says, slice up the horizontal axis into little intervals, build a thin rectangle on each one, and add up the areas. The height of each rectangle is determined by the value of the function somewhere inside that interval. Make the intervals narrower and narrower, and if the sum of those rectangles settles down to a single number, that's your integral. It's a beautiful idea, and it works wonderfully for most functions you'd encounter in everyday math or physics. But here's the key detail. Riemann is slicing up the domain, the input side, the x-axis. He's partitioning the horizontal direction and then asking, what does the function do on each little slice? Leibniz flipped that completely on its head. Instead of slicing up the x-axis, he sliced up the y-axis. Instead of asking, what does the function do on this little interval of inputs, he asked, where does the function take this particular range of values? Think about that for a second, because it's a genuinely different way of looking at the same problem. Imagine you're trying to figure out how much a company pays in total salaries. Riemann's approach would be like going office by office, floor by floor, writing down each person's salary as you encounter them, and adding it all up. Leibniz's approach would be like saying, okay, how many people earn between 30 and 40,000? How many earn between 40 and 50,000? Between 50 and 60? You group people by salary range, count how many fall in each group, multiply the salary by the count, and add those up. You get the same total, but the method of organizing the calculation is fundamentally different. And here's why that matters. When you organize by salary range, when you slice up the y-axis instead of the x-axis, you can handle situations that are way more chaotic. Think about a function that jumps around wildly, taking different values in an incredibly erratic way across its domain. If you try to slice up the x-axis into little intervals, the function might be doing something completely unpredictable on each interval, and Riemann's rectangles just can't get a grip on it. But if you instead ask, where does the function take values between, say, 3 and 3.1? You're gathering up all the scattered places in the domain where the function falls in that range. They might be spread all over the place, not forming any nice interval at all, and you're measuring how much of the domain they occupy. That measurement of how much of the domain is the crucial innovation. It requires a more sophisticated way of measuring the size of sets than just length. You need what mathematicians call a measure. Leibniz developed this in his 1902 doctoral thesis at the University of Paris, and it's one of those dissertations that genuinely changed the landscape of mathematics. He was building on earlier work by Émile Borel, who had started developing a theory of measure for sets of real numbers in the late 1890s. But Leibniz took it much further. He defined what's now called Leibniz measure, which assigns a size to an incredibly wide class of subsets of the real line, not just intervals, but complicated, fragmented, scattered sets that you could never describe with simple geometry. And once you have that measure, you can define the integral in this new way. Partition, the range of the function. Look at the pre-image of each partition piece. That is, the set of all inputs that map into that piece. Measure the size of that pre-image using Leibniz measure, multiply by the value, and sum up. The result is an integral that can handle far more functions than Riemann's. Every function that's Riemann integrable is also Lebesgue integrable, and you get the same answer. But there are functions that Lebesgue can integrate that Riemann simply cannot. The classic example is the function on the interval from 0 to 1 that equals 1 at every rational number and 0 at every irrational number. This thing is discontinuous everywhere, at every single point. Riemann's integral completely chokes on it, but Lebesgue's integral handles it effortlessly. The set of rational numbers in that interval, despite being infinite, even densely packed in the sense that there's a rational between any two reals, has Lebesgue measure 0. The irrationals have measure 1. So the integral just comes out to 0 times 0 plus 1 times. Wait, let me say that more carefully. The function is 1 on a set of measure 0 and 0 on a set of measure 1. So the integral equals 1 times 0 plus 0 times 1, which is 0. Clean, simple, done. Now you might be thinking, okay, that's a neat trick for a pathological function that nobody would ever encounter in real life. And fair enough. You're not going to run into that particular function while designing a bridge. But here's the thing. The power of Lebesgue's integral isn't really about integrating weird functions for the fun of it. It's about the theorems you can prove. The Lebesgue integral has much, much better theoretical properties than the Riemann integral. Specifically, it plays beautifully with limits. Remember those questions that kept coming up. Can you interchange a limit and an integral? If you have a sequence of functions that converge to some limiting function, does the integral of the limit equal the limit of the integrals? With Riemann's integral, you need very strong conditions for that to work. With Lebesgue's integral, you get powerful theorems, the monotone convergence theorem, the dominated convergence theorem, that give you much more freedom to swap limits and integrals, and that freedom is absolutely essential in modern analysis, in probability theory, in quantum mechanics, in signal processing, in basically every serious application of mathematics that involves infinite processes, which is nearly all of them. This is one of those moments where the story of calculus connects directly to the story of physics in the 20th century. When quantum mechanics was being formulated in the 1920s and 1930s, the mathematical framework it needed was something called Hilbert spaces, infinite dimensional spaces where you can do geometry with functions instead of arrows. The inner product in these spaces, the thing that lets you measure angles and distances between functions, is defined using integrals. And it has to be the Lebesgue integral, not the Riemann integral, because you need those convergence theorems to make the whole structure work. When John von Neumann wrote his rigorous mathematical foundations of quantum mechanics in 1932, Lebesgue integration was baked right into the framework. Without it, the math simply doesn't hold together. So here's this quiet French mathematician writing his thesis in 1902, and he's building a tool that will become indispensable to the physics of atoms and particles 2 and 3 decades later. He couldn't have known that. Nobody could have. And that's one of the recurring themes in this whole story. The way pure mathematical ideas developed to solve what seem like abstract puzzles about the foundations of calculus turn out to be exactly what's needed when science pushes into new territory. But let's pull back from the abstract for a moment and think about what calculus looked like in the early 20th century from a broader perspective. By this point, roughly 1900 to 1920, calculus wasn't just a subject anymore. It had branched and grown into an entire ecosystem of mathematical disciplines. There was real analysis, which is what we've been talking about. The rigorous study of limits, continuity, differentiation, and integration on the real numbers. There was complex analysis, the study of calculus applied to functions of complex numbers, which had been developed extensively by Cauchy, Riemann, and Weierstrass, and which turned out to have almost magical properties. Complex differentiable functions are automatically infinitely differentiable. automatically equal to their own power series, automatically determined everywhere by their values on any small region. There was differential geometry, which used calculus to study curved surfaces and spaces, pioneered by Gauss and Riemann, and eventually providing the mathematical language Einstein needed for general relativity in 1915. There was the calculus of variations, which asks not for the value that minimizes a function, but for the entire function or curve that minimizes some quantity. The path of least time, the shape of least area, the trajectory of least action. There were differential equations, ordinary and partial, which had grown into enormous fields of their own, essential to every branch of physics and engineering. All of these grew from the same seed, from that fundamental insight that Newton and Leibniz had crystallized in the 17th century, the insight that you can make sense of instantaneous change, and that the two great operations of calculus, differentiation, and integration are inverses of each other. Every one of these branches relies on that core relationship, and every one of them was made rigorous, made trustworthy, made precise by the foundational work of Cauchy, Weierstrass, Dedekind, Cantor, Riemann, and Lebesgue. There's something deeply satisfying about that arc. For 200 years, from roughly 1665 to 1870, calculus worked. It gave correct answers. It solved real problems. It predicted the motions of planets and the shapes of vibrating strings and the flow of heat through metal. But nobody could fully explain why it worked. The foundations were shaky. The infinitesimals were ghostly. The proofs had gaps. And then, in a concentrated burst of creative energy spanning maybe 50 years, a handful of mathematicians rebuilt the entire edifice on solid ground. They didn't change what calculus could do. They changed what calculus was. They turned it from a collection of powerful techniques into a rigorous mathematical theory. And once that was done, once the foundations were secure, mathematicians could push further than ever before. They could generalize. They could abstract. They could ask, what if we do calculus not on the real line, not on the plane, not even on three-dimensional space, but on more exotic spaces? What if the points in our space are functions or sequences or probability distributions? What if the space is curved or infinite dimensional or has a strange topology? These questions drove 20th century mathematics into extraordinary new territory, and they all depended on having those foundations in place. One of the most profound of these generalizations came from the world of differential equations, and it connects directly to something you experience every single day without thinking about it. When you listen to music through headphones, or when your phone compresses a photo, or when a doctor looks at an MRI scan of your brain, there's a piece of mathematics working behind the scenes that grew directly out of the calculus of the 18th and 19th centuries. It's called the Fourier transform, and its story begins with a problem about heat, specifically with a French mathematician and physicist named Joseph Fourier, who was trying to understand how heat flows through a solid object. Fourier's life, by the way, is one of those stories that seems almost too dramatic to be real. He was orphaned as a child, educated by Benedictine monks, became a teacher, got swept up in the French Revolution, nearly lost his head to the guillotine, literally, accompanied Napoleon on the Egyptian campaign, served as a governor in France, and somehow, through all of that chaos, managed to produce one of the most important mathematical works of the 19th century, his masterpiece, the Théorie analytique de la chaleur, the analytical theory of heat, published in 1822, though the core ideas had been circulating since around 1807, when he first presented them to the French Academy. And the reception was complicated, because what Fourier claimed in that work struck some of the greatest mathematicians of his era as genuinely suspect. Here's the problem he was trying to solve. You have a metal bar, or a metal plate, or some solid body, and one part of it is hot, while another part is cold. Heat flows from the hot region to the cold region. Everyone knew that. But Fourier wanted to describe that flow precisely, mathematically, as a function of position and time. He derived what we now call the heat equation, which is a partial differential equation. It relates how the temperature at any point changes over time to how the temperature varies across space at that same moment. The equation itself is elegant, and it captures something physically intuitive. The rate at which a point heats up or cools down depends on the difference between its temperature and the temperatures of its neighbors. If you're hotter than everything around, you cool down. If you're cooler, you warm up. The heat equation makes that precise. But here's where Fourier did something radical. To solve the heat equation for specific situations, say a metal ring with some initial temperature distribution, he proposed that you could express essentially any function as a sum of sines and cosines, not just smooth, well-behaved functions. Any function. You could take some jagged, irregular initial temperature profile and break it down into a combination of simple waves, each with its own frequency and amplitude, and when you added all those waves together, they'd reproduce the original shape. This is what we now call a Fourier series, and the mathematicians of his day, including Lagrange, who was on the review committee, were deeply skeptical. Lagrange basically said, "No, you can't do that. It's not valid." The idea that you could represent a discontinuous function, a function with sharp corners or jumps, as a sum of perfectly smooth sine and cosine curves seemed almost paradoxical. How can you add up smooth waves and get something with a sharp corner? It feels wrong. But Fourier insisted it worked, and he could show it working in specific cases, and eventually the mathematical community came around, though it took decades to sort out the precise conditions under which Fourier series converge to the function they're supposed to represent. That convergence question, by the way, was one of the things that drove Riemann and later mathematicians to think more carefully about integration and the structure of functions. So Fourier's bold claim didn't just solve the heat equation, it forced mathematics itself to grow. Now, think about what Fourier was really saying. He was saying that any signal, and I'm using the word signal loosely here, any function that varies over time or space can be decomposed into pure frequencies. It's like saying any sound, no matter how complex, is really just a combination of pure tones, a symphony orchestra playing a massive chord. Mathematically, you can break that down into individual sine waves, each at a specific frequency, each with a specific loudness. Your ear actually does something like this. The cochlea in your inner ear has tiny hair cells that respond to different frequencies, so your biology is performing a kind of Fourier analysis every time you hear anything. The Fourier transform takes this idea and extends it beyond periodic functions to functions that don't repeat. A Fourier series works for functions that repeat, periodic functions, by decomposing them into discrete frequencies, this much of the first harmonic, this much of the second, and so on. But the Fourier transform handles functions that stretch out over all of time or all of space without repeating, and instead of giving you a list of discrete frequencies, it gives you a continuous spectrum. It tells you how much of each frequency is present in your signal. You put in a function of time, and you get out a function of frequency. You're looking at the same information from a completely different angle. And this is where it connects to your everyday life in ways that are almost hard to overstate. When your phone stores a digital photo, it uses a variant called the discrete cosine transform, a close cousin of the Fourier transform, to figure out which spatial frequencies are present in the image. Smooth areas of the photo have mostly low frequencies. Sharp edges and fine details have high frequencies. The compression algorithm then throws away the highest frequencies that your eye won't really miss, which is why JPEG files are so much smaller than raw images. The math Fourier developed to understand heat flow in 1807 is the reason you can text a photo to someone without it eating up all your data. MRI machines, magnetic resonance imaging, work on a similar principle. The machine doesn't directly photograph the inside of your body. Instead, it measures radio signals emitted by hydrogen atoms in your tissues when they're placed in a strong magnetic field, and those signals come in as a jumble of different frequencies. A Fourier transform converts that frequency data into spatial information, into the actual image the doctor looks at. Without the Fourier transform, MRI doesn't exist, and that means a huge swath of modern medical diagnosis traces its mathematical ancestry back to a French orphan who was fascinated by heat. So, that's one thread of how calculus matured and spread in the 20th century, through Fourier analysis and signal processing. But let's pull on another thread, because this one is equally remarkable, and maybe even more surprising in its origins. Let's talk about how calculus learned to handle randomness. If you think about the calculus we've been discussing, Newton's fluxions, Leibniz's differentials, Cauchy's limits, Weierstrass's epsilon delta proofs, all of it deals with functions that are, in some sense, well behaved enough to differentiate or integrate. Even the pathological functions that Weierstrass constructed, the ones that are continuous everywhere but differentiable nowhere, were understood as edge cases, curiosities that tested the boundaries of the theory. But in the early 20th century, mathematicians and physicists started encountering a new kind of mathematical object that was far wilder than anything Weierstrass had dreamed up, and it came from the most physical, most concrete source imaginable: the random jittering of tiny particles suspended in liquid. In 1827, the botanist Robert Brown looked through a microscope at pollen grains suspended in water and noticed that they jiggled around in an erratic, unpredictable way. This became known as Brownian motion. For decades, nobody could fully explain it. Then in 1905, the same miracle year when Einstein published his papers on special relativity and the photoelectric effect, he also published a paper explaining Brownian motion as the result of water molecules constantly bombarding the pollen grains from all sides. The pollen grain gets hit by millions of molecules every second, and because those hits are random, the grain follows a jagged, wandering path. Einstein's analysis was brilliant, and it helped confirm the existence of atoms, which was still debated at the time. But from a mathematical standpoint, the path traced by a Brownian particle is deeply strange. Here's what's wild about it. The path is continuous. The particle doesn't teleport from one place to another. But it's nowhere differentiable. Nowhere. At no point along its path can you define a velocity in the classical sense, because the path is so jagged, so fractal-like, that no matter how much you zoom in, it never smooths out. It's like Weierstrass's pathological function, but it shows up in nature, in real physical systems. you can watch it happen under a microscope. This created a genuine problem for calculus. If you want to model financial markets, or diffusion processes, or population dynamics with random noise, you need to do calculus on paths like these, paths that are continuous but nowhere differentiable. You need to integrate along them, define equations involving them. But the classical tools don't work, because those tools assume a certain amount of smoothness. The person who cracked this problem was a Japanese mathematician named Kiyoshi Ito. Working in the 1940s and 1950s, Ito developed what's now called stochastic calculus, a version of calculus specifically designed to handle random, non-differentiable processes. His key innovation, the Ito integral, defines integration along Brownian paths in a way that respects their randomness. It's not a straightforward extension of Riemann or even Lebesgue integration. You have to be very careful about how you set it up, because the random fluctuations mean that the order in which you evaluate things matters in ways it doesn't in ordinary calculus. The Ito integral and the stochastic differential equations built on top of it became absolutely foundational in multiple fields. In physics, they describe diffusion and noise in everything from semiconductor devices to stellar dynamics. In biology, they model population fluctuations and the random drift of gene frequencies. But perhaps the most famous and most consequential application came in finance. In 1973, Fisher Black, Myron Scholes, and Robert Merton used Ito's stochastic calculus to derive the Black-Scholes equation, a formula for pricing financial options. That equation transformed Wall Street. It enabled the explosive growth of the derivatives market, which grew to trillions of dollars. Scholes and Merton won the Nobel Prize in economics for it in 1997. The mathematics of Brownian motion, of pollen grains jittering in water, became the engine of modern financial markets. And you can trace the lineage directly. Newton and Leibniz create calculus. Cauchy and Weierstrass make it rigorous. Weierstrass discovers pathological functions. Einstein describes Brownian motion. Wiener formalizes the mathematics of random paths. Ito invents stochastic calculus. Black, Scholes, and Merton use it to price options. Each step depends on the one before it. The chain is unbroken. Now there's another direction the calculus expanded in the 20th century that I want to touch on, because it brings us to something that might be the most powerful application of calculus alive today, and it's probably running on a computer within arm's reach of you right now. I'm talking about the way calculus powers machine learning and artificial intelligence, and the specific technique at the heart of it is something called gradient descent. The idea is surprisingly simple, and it connects directly back to the optimization problems that Fermat was thinking about in the 17th century, finding maxima and minima, finding where a derivative equals zero. But the scale at which it operates today would have been unimaginable to anyone before the age of computers. Imagine you have a function, not a function of one variable, or two, or three, but a function of millions of variables. Each variable represents a parameter in a neural network, a weight or a bias that determines how the network responds to input. The function measures how wrong the network's predictions are. It's called a loss function, and you want to minimize it. You want to find the combination of millions of parameters that makes the network's errors as small as possible. That's an optimization problem, and calculus gives you the tool to solve it. You compute the gradient, the multidimensional version of the derivative, which tells you, at your current position in this million-dimensional landscape, which direction is downhill. Then, You take a small step in that direction. Then you compute the gradient again and take another step, and another, and another. You're descending the slope of this vast, complicated surface, trying to find a valley, a minimum, a place where the loss is low and the network's predictions are good. The algorithm that makes this practical for neural networks is called backpropagation, and it's essentially an efficient application of the chain rule, the same chain rule that Leibniz's notation made so intuitive 3 centuries ago. When you have a neural network with many layers, the output depends on the parameters of the last layer, which depend on the outputs of the previous layer, which depend on its parameters, and so on, all the way back to the input. Computing the gradient of the loss with respect to every single parameter means applying the chain rule over and over, propagating the derivative backward through the network layer by layer. It's the chain rule at industrial scale. And here's what's remarkable. Every time a large language model generates a sentence, every time an image recognition system identifies a face, every time a recommendation algorithm suggests a video, the system doing that work was trained using gradient descent and backpropagation. Calculus, the same calculus that Newton used to describe planetary orbits, that Fourier used to understand heat, that Ito extended to handle randomness, is running behind the scenes of technologies that billions of people interact with every day. The derivative, that simple idea of instantaneous rate of change, has become one of the most practically consequential mathematical ideas in human history. And if you think about it, that's a strange and beautiful arc, an idea born from trying to understand how things move and change, how a planet sweeps through its orbit, how a curve bends at a single point, has become the engine-driving machines that learn to see, to speak, to translate, to create. But here's the thing. Gradient descent, powerful as it is, isn't some magic bullet. It has real limitations, and the story of how people have wrestled with those limitations over the last few decades is itself a story about calculus evolving, being pushed into new territory, being asked to do things its inventors never imagined. So let's stay with this for a little while, because it's worth understanding what happens when you try to navigate a landscape with 1,000,000 dimensions, armed with nothing but a derivative and a willingness to take small steps. The first problem is obvious once you think about it. Gradient descent finds a minimum, but it finds a local minimum. Imagine you're on a hilly landscape in fog so thick you can only feel the ground immediately under your feet. You walk downhill, you reach a valley, you stop. But is it the deepest valley? You have no idea. There might be a much deeper valley on the other side of a ridge you can't see. In a 1,000,000-dimensional loss landscape, there are an astronomical number of these local minima, plus saddle points, places that look like minima in some directions, but are actually just flat spots along a ridge. For years, people worried that neural networks would get stuck in bad local minima and never find good solutions. And here's what's kind of surprising. In practice, for very large networks, this turns out to be less of a problem than you'd expect. The mathematical intuition, developed by people studying high-dimensional random surfaces, work connected to statistical physics and random matrix theory, suggests that in very high dimensions, most local minima are actually pretty close in quality to the global minimum. The bad local minima, the really deep but isolated traps, become increasingly rare as the number of dimensions grows. It's one of those cases where higher dimensions, which seem like they should make everything harder, actually help in a strange way. But there are other challenges. The gradients themselves can misbehave. In deep networks, networks with many layers, The chain rule gets applied so many times that the gradients can either explode or vanish as they propagate backward through the layers. Think about multiplying a number by something slightly greater than 1 over and over. It gets huge fast. Multiply by something slightly less than 1 over and over. It shrinks to nothing. That's essentially what happens with gradients in deep networks. If the derivatives at each layer are consistently a bit larger than 1, by the time you've propagated back through 50 or 100 layers, the gradient has blown up to astronomical values. If they're consistently a bit less than 1, the gradient has decayed to effectively 0, and the early layers of the network learn nothing. They receive no useful signal about how to adjust. This is the vanishing gradient problem, and it plagued deep learning for years. It's one of the main reasons people struggled to train networks with more than a few layers throughout the 1990s and into the 2000s. The solutions that emerged are clever, and they're all, at their core, about managing the behavior of derivatives. One approach, popularized around 2010 and after, was to use activation functions, the nonlinear functions applied at each neuron, that don't squash their inputs into a narrow range. The old favorite was the sigmoid function, which maps everything into a range between 0 and 1. Beautiful, smooth, differentiable. But its derivative is very small for large positive or negative inputs, which means gradients die as they pass through it. The fix was almost embarrassingly simple. Use a function called ReLU, rectified linear unit, which just outputs 0 for negative inputs and the input itself for positive inputs. Its derivative is either 0 or 1, no squashing. Gradients flow through cleanly. It's a piecewise linear function, barely even interesting looking, and yet switching to it was one of the key practical breakthroughs that made deep learning work. Calculus doesn't care whether a function is elegant. It just needs the derivative to behave well. Another solution was architectural. In 2015, Kai-Ming He and his colleagues introduced residual networks, ResNets, which added skip connections that let the gradient bypass layers entirely, flowing directly from later layers to earlier ones through shortcut paths. The mathematics is straightforward. If you add the input of a block directly to its output, then the gradient with respect to that input includes a term that's just 1. It passes through unchanged, undiminished. It's a structural trick that keeps the chain rule from compounding those small multiplicative factors, and it worked spectacularly. ResNets could be trained with over 100 layers, then hundreds of layers, depths that would have been unthinkable just a few years earlier. So when you hear about the latest AI breakthrough, a model with billions of parameters, trained on enormous data sets, know that underneath all the engineering and all the clever tricks, the fundamental operation is still compute a derivative, take a step, repeat. The scale is breathtaking, the implementation is sophisticated, but the mathematical heartbeat is calculus, and that brings us to something worth reflecting on as we wind toward the end of this long, winding story. Calculus didn't arrive in the world fully formed. It wasn't handed down complete. It was built, piece by piece, over centuries, by people who were often working on very specific, very practical problems and had no idea how far their ideas would travel. Archimedes wanted to find the area under a parabola. That's it. He wasn't trying to invent a universal theory of integration. He was solving a geometry problem using the most ingenious method he could devise: exhaustion, squeezing the answer between bounds that got tighter and tighter. But that impulse, that instinct to approach a curved thing by approximating it with straight things and then asking what happens in the limit, That's the seed of everything that came after. Fermat wanted to find the maximum and minimum values of algebraic expressions. He developed a technique that looks, in hindsight, almost exactly like taking a derivative and setting it equal to zero. He didn't have the language for it. He didn't have limits, didn't have a formal definition of the derivative. But he had the idea, the essential move, and it worked. Newton needed to understand motion, real, physical motion. Objects falling, planets orbiting, light refracting. He needed a mathematics that could handle continuous change, and when he couldn't find one, he built it. His fluxions were tied to his physics, inseparable from it. The math and the science grew together in his mind, each feeding the other. And whatever you think of Newton the person, difficult, secretive, vindictive in his priority disputes, the sheer scope of what he accomplished in those plague years at Woolsthorpe is almost incomprehensible. He was in his early 20s. He invented calculus, laid the foundations of classical mechanics, and made fundamental discoveries about light and optics, essentially in isolation, essentially because he was curious and had nothing else to do. Leibniz came at it from a different angle, more philosophical, more concerned with notation and generality, more interested in building a calculus that other people could actually use. And his notation won, not because it was flashier, but because it was genuinely better at capturing the structural relationships that make calculus work. That dy over dx, that integral sign, they're not just symbols. They encode the logic of the operations in a way that guides your thinking, that makes the chain rule almost write itself. Good notation isn't decoration. It's a tool for thought. Then came the long, beautiful, sometimes painful process of making it all rigorous. Berkeley pointed out, correctly, that the foundations were a mess, and it took more than a century to clean them up. Cauchy with his limits, Weierstrass with his epsilons and deltas, Dedekind and Cantor with their constructions of the real numbers. That work wasn't glamorous. It didn't produce new physical predictions or solve engineering problems. But it mattered enormously because it meant that when mathematicians pushed calculus into strange new territories, infinite dimensional spaces, stochastic processes, abstract manifolds, they could do so with confidence that the foundations wouldn't crack beneath them. And push they did. Fourier used calculus to understand heat. Riemann generalized the integral, and in doing so, opened up questions about the structure of functions that nobody had thought to ask. Lebesgue rebuilt integration from the ground up, measuring sets instead of slicing intervals, and his version turned out to be exactly what 20th century physics and probability theory needed. Von Neumann used it to give quantum mechanics a rigorous mathematical framework. Ito extended the derivative and the integral into the realm of randomness, creating a calculus for processes that jitter and jump, and that stochastic calculus became the language of modern finance and much of modern science. Each of these steps was built on the ones before it. Each one extended the reach of the original idea, that you can understand the world by looking at how things change, instant by instant, and by adding up infinitely many, infinitely small pieces to find the whole. That double insight, differentiation and integration, connected by the fundamental theorem, has turned out to be one of the most versatile and powerful frameworks human beings have ever created. And here's what I find most remarkable, the thing I keep coming back to when I think about this story. Calculus works. It works unreasonably well. It describes the trajectory of a thrown ball and the evolution of a galaxy. It predicts the behavior of electrical circuits and the spread of diseases through populations. It underlies the design of every airplane wing, every suspension bridge, every MRI machine. It trains the neural networks that recognize your face in photos and translate languages in real time. The same fundamental ideas, limits, derivatives, integrals, keep showing up century after century in application after application, far beyond anything their inventors could have foreseen. There's a famous essay by the physicist Eugene Wigner, published in 1960, called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. Wigner marveled at the fact that mathematical structures developed for purely abstract reasons kept turning out to be exactly the right tools for describing physical reality. Calculus is perhaps the most dramatic example of this. It was developed to solve specific problems in geometry and physics, but it turned out to be woven into the fabric of how the universe works at almost every scale and in almost every domain. Maybe that's because change itself is universal. Everything changes. Everything flows. Heraclitus said that 2,500 years ago, and he was right. The temperature of your coffee is changing right now, cooling toward room temperature according to a differential equation Newton himself wrote down. The air pressure outside your window is fluctuating, governed by the Navier-Stokes equations. Partial differential equations that are so difficult, proving basic facts about their solutions is one of the Millennium Prize problems, worth $1 million to anyone who can crack it. Your own body is a symphony of change, cells dividing, signals propagating along nerves, chemicals diffusing across membranes, all of it describable in principle by the language of calculus. So as you lie there, maybe drifting, maybe already half asleep, here's what I want you to carry with you, or let go of, whichever feels right. Calculus is not just a subject you take in school. It's not just a collection of rules for differentiating and integrating functions. It's a way of seeing the world, a lens that reveals the hidden structure of change. It connects the instantaneous to the cumulative, the local to the global, the way things are right now to the way they'll be, a moment from now. And that connection, that bridge between the infinitely small and the finitely whole, has been built and rebuilt and extended by centuries of human effort, by people who were curious and stubborn, and sometimes wrong, and sometimes brilliant, and always, always reaching for something just beyond what they could see. The story isn't over, of course. It never is. Right now, mathematicians and physicists and computer scientists are extending calculus in directions we can barely glimpse. Fractional calculus, where you take half a derivative. Calculus on graphs and networks, where the underlying space isn't smooth at all. New computational methods that let us solve equations that were intractable a decade ago. The tool keeps growing, keeps adapting, keeps finding new problems to illuminate. But for tonight, this is a good place to rest. The river of ideas that started with Archimedes, drawing curves in the sand of Syracuse, has carried us a very long way, through Newton's orchard and Leibniz's study, through the rigor of Cauchy and Weierstrass, through Fourier's heat and Ito's randomness, all the way to the neural networks humming in data centers right now, learning and adjusting, one gradient step at a time. It's all one story. And the beautiful thing about it is that it's still being written. So let that thought settle, if you like, or let it drift away. Either way, the math will still be there in the morning, quietly describing the way the world changes, the way it always has, the way it always will. Good night.